Today we will start chapter 5, okay? Chapter 5. And at the end of chapter 5, I will give you a test. Okay? The test includes chapter 5 and the Lotus rule, okay? The Lotus rule. So now, first we record the Lotus rule. So the Lotus rule means what? Means the indeterminate form of time 0 divided by 0. Yeah?
Yes.
Here, first, if a function x approaches a, fx approaches 0, and x approaches a, gx approaches 0. Yeah, and if limit x approaches a, f prime fx divided by g prime, this limit required, okay? Required. If this limit exists, or is plus infinity or minus infinity. If we have these three conditions, then we have what? Then we have limit x approaches a, fx divided by gx. This limit equal to what? Equal to limit x approaches a, f prime divided by g prime. Okay? G prime. So this is the indeterminate form of 0 by 0. And we have infinity by infinity, yeah? So infinity by infinity. So if here is infinity, here is infinity, yeah? And x approaches a, f prime divided by g prime. This limit exists. Then we have this conclusion, okay? So we have these two indeterminate forms. And then we have 0 times infinity, yeah? 0 times infinity. For this indeterminate form, we first need to transfer it to 0 by 0 or infinity by infinity, yeah? So here we just need to write 0 equal to what? 0 equal to 1 by infinity, or infinity equal to 1 by 0. Yeah? We use these two formula. We can transfer 0 times infinity equal to 0 by 0 or infinity by infinity. Okay? And we introduce the 0 infinity minus infinity for this form, okay? For this form, first you must make them have the same denominator, and then you can see the numerator and the denominator is in this form, okay? And we have another for 0 to the power 0, 1 to the power infinity, yeah? So infinity to the power 0. So for this three, okay? For this three, just keep in mind, okay? We first take the ln on both sides. take log on both sides and transform it to 0 by 0 or infinity by infinity. So you keep in mind that. Keep in mind that. So you keep in mind that if you have you need to find a limit, use the L'Hopital's rule. The first step is you must to determine is 0 by 0 or infinity by infinity. If it's 0 by 0 or infinity by infinity, you can use this convolution. If not, you cannot use this convolution, okay? So we have two steps, okay? Two steps. The first step is determine it's 0 by 0, infinity by infinity, and write it in this form, okay? Write it in this form. So this is the L'Hopital's rule. Today we will start the chapter 5, okay? See the book, page 210. 210. So number 5, chapter 5, okay? Chapter 5 is the derivative in graphy and applications. Page 210. 210. So today we will introduce the increasing and decreasing and concavity and concavity. So now first we see a graph. We see a graph. For example, for this graph. For this graph, okay? For this graph, here we can see this point x coordinate here is 2, here is 2, and this here is 0, here is 0, here is 2, and here is 4, and here is 4. So we can see that here in this part, okay, in minus infinity to 0, the graph is increasing, and to 0 to 2, okay, from 0 to 2, the graph is goes down, decreasing, okay, decreasing, and from 2 to 4, the here is increasing, yeah, it's go close, yeah, and from 4 to infinity, here actually is a play, yeah, the play. So here means what? Here means it is a constant, okay? The function is a constant. So here now, so we need to describe the increasing and the decreasing. So how to describe the increasing and decreasing? So here from here we can see if we okay, in this part, okay, in this increasing part, we can see in this part. If here is x1, here is x2, here is x2. So we can see if x1 less than x2, if x1 less than x2, if it is increasing, here means what? Here means the fx1 less than fx2, okay? So here this part increasing. In the increasing part, we have this convolution, and in the decreasing part, okay, in the decreasing part, actually, if here, for example, here is x3, here is x4, so we can see here x3, x4. If x3 is less than x4, yeah. So in decreasing part, we have what? We have fx3 is greater than fx4. Yeah? In this decreasing part, okay? And in this constant part, In this constant part, for example, here is x5, here is x6, here is x6. So here means what? Here means fx5 equal to fx6 for any x5 and x6. So here means for any 2 points, if the function is a constant, we have what? We have fx5 equal to fx6. Okay. So from here we can have the definition of the increasing and decreasing. So now let's see. Let's see a graph here. Here is x, y. Here is the original. So here, in this part, here is the left point is A, the right point is B. So here is increasing, increasing. So in this part, so we take x1. We take x1 and x2, x2. So here is increasing. Yeah. For this increasing, we have a conclusion. If x1 less than x2, then we have what? Then we have fx1 less than fx2. So here, this is the definition. This is the definition of increasing. So what about the decreasing? Actually, the decreasing is so the decreasing, for example, here. Here is A, here is B. So here is x1, x2. So here we take for any x1 less than or for any x1, x2 belongs to the interval AB. For any x1, x2 belongs to the interval AB, and x1 less than x2. If fx1 less than x2, then we have what? Then we have fx1 greater than fx2. So here this actually is the definition of the decreasing. The decreasing. So what about the last one? The last one is a constant. A constant means here is a plane. So here actually the left is also A. Here is B. So here means what? Here means here x1, x2. So for any x1, x2 belongs to the interval AB, we have fx1 equal to fx2 for any x1, x2, for any x1, x2. So here means for any x1, x2, we have fx1 equal to fx2. So this is the definition of a constant function. So we can rewrite it in a definition which actually this part is on the book, okay? On the book. So here we have the definition. We have the definition. The definition, let f be defined on an interval and let x1, x2 denote points in that interval. Then we have f is increasing on that interval. If fx1 less than fx2, whenever x1 less than x2, okay? So here is increasing. If f is increasing on that interval, means fx1 less than fx2, whenever fx1 less than x2, okay? So here the second, f is decreasing on that interval if fx1 greater than fx2, whenever x1 less than x2, okay? Less than x2. And the third, okay? The third means f is a constant. F is a constant on that interval if fx1 equal to fx2 for all points x1 and x2. So here, actually, this is the definition. Okay, this is the definition. So we have a question. Now we have the definition of the increasing, decreasing, and the constant. So how to find if I give you a function, how to find the function is increasing or decreasing or constant? Actually, a constant is easy, yeah, it's easy. But how to see the function is increasing or decreasing, or see the increasing interval, decreasing interval, yeah, decreasing interval. So for example, for y equal to x squared, for this function, we know the graph. We know the graph is like this, yeah. So here we can see we plot the graph, and it's easy to see that the graph actually is decreasing in the interval minus infinity to 0. In this interval, this function is decreasing, yeah. And in 0 to plus infinity, in this interval, the function actually is increasing, yeah, it's increasing. So if the function is, you can easy to plot the graph, and you can easy to see the increasing, decreasing. But sometimes it's not easy to plot the graph. So how to determine the increasing interval and the decreasing interval? So now we need to find another method, okay? Another method. So here for this part, okay? For increasing, for this part we can see here. If we see the touched line, okay? The touched line on any point of this graph, we can see this is the attached line, yeah? So this is the attached line. So at this point, we can see this attached line, the slope is positive. Yeah, the slope is positive. The slope is positive, okay? Increasing, okay? Increasing, we can see at this point. At any point actually, at any point of the increasing graph, we can easily see that the slope is positive. The slope is positive. And now for the decreasing, we can see here, for any point, for example, for this point, the slope actually of the pattern actually is like this. It's like this. So it's easy to see the slope actually is negative, yeah? The slope is negative. The slope is negative. So the slope is negative. And now for the constant, okay? For the constant, actually for any point here, for any point the tangent line actually is a plane, yeah? So here means for this point is a constant. So the slope here actually is what? Here is plane, here is go down, here is go up. Go up, so positive. Go down, yeah? So it's negative, yeah? So it's a plane, so it's 0, yeah? So the slope is 0. Slope is 0. So here, from here, we can see, can we use the slope? Can we use the slope to determine is increasing, decreasing, or constant? Actually, we can. Okay, we can. So first, the slope actually is what? The slope actually is the derivative. Yeah. Yeah. So the slope of the tangent line at this point actually is the derivative at this point. Yeah. So here means what? Here this slope actually is f prime. F prime x. Here this is the slope. Yeah. The slope positive means greater than 0. Yeah. Greater than 0. So here means if the derivative is positive, then the function here is increasing, and here the slope negative means less than 0. If the slope less than 0 means the function is decreasing. And then the slope is 0. So the slope is 0, so means this function at this constant is a constant. So here we have a method, okay? An important method to determine the function is increasing, decreasing, or constant. So we use the derivative. So we have this result, okay? We have this result. now we can see this result, okay? This result. Let f be a function that is continuous on a closed interval AB, okay, AB, and definable on the open interval AB, okay, AB. So if f prime greater than 0, for any, okay, here is any, for any x belongs to AB, here is the open interval, then f is increasing on closed interval AB. So if f prime less than 0, for any, okay, for any x belongs to AB, belongs to open interval AB, then f is decreasing on the closed interval AB, okay? If f prime equal to 0, for any x equal to for any x belongs to AB, then f is constant, okay? Then f is constant. So here we can use what? This result tells us that you can use the derivative, positive, negative, or 0 to see that the function is increasing or decreasing or constant at that interval, okay? On that interval. So here you must, here means greater than 0, increasing, less than 0, decreasing, equal to 0, constant. Okay, here is any, okay?
Yes.
Any. So here now I give an example. So here, find the intervals on which fx equal to x squared minus 4x plus 3, and gx equal to 3x to the fourth power plus 4x cubed minus 12x squared plus 2. Okay? It's increasing, and the intervals on which it's decreasing. Okay. So actually we use the result. We just need to do one thing. Okay. Do one thing first. Find the derivative. And to see on each on which interval the derivative is positive, negative, or 0. So just do this thing. Okay. One thing is easy. Yeah. So now first, we see the fx, okay? Fx equal to x squared minus 4x plus 3, yeah? For this function? So the derivative is what? So the derivative f prime equal to what? Yeah? 2x. And minus 4, yeah? Minus 4, 2x minus 4, so equal to, we can take 2 out. So 2 times x minus 2, yeah? So it's easy to see here, where x greater than 2 is positive, where x less than 2 is negative, yeah? So here we can see where x, so here we can list a table, okay? We can list a table this table like this. Here, the first, here is the interval, here is the interval, here is the f prime, here is the conclusion, okay? So here, the interval, here we can see, the interval we see is minus infinity to 2, yeah? So the first interval is minus infinity to 2, yeah? So in this interval, the f prime is negative or positive? Negative, yeah? So here means f prime here is less than 0, less than 0. So the conclusion is decreasing, yeah? So the conclusion is decreasing. So the second interval is 2 plus infinity, yeah? 2 plus infinity. So the f prime here is greater than 0, yeah? Greater than 0. So the conclusion actually is increasing, yeah? So I think it's so easy, yeah? So easy, yeah? So of course I will test it at the user exam, okay?
Okay.
So I think you should be happy, yes? So this is the first, okay? The first fx. The second here, the gx. The second gx. Now let's see the gx. The gx equal to 3x to the first power plus 4x or 4x cubed minus 12x squared plus 2. Yeah? Plus 2. So the first step you need to find the derivative. Yeah?
Yeah.
So the derivative g prime equal to what? 12x cubed. Yeah? 12x cubed plus 5x squared, yeah, and minus 24x, yeah, plus 0, yeah, plus 0. So here we can 12 times 24 x cubed x squared x. So we can take out what? We can take out 12x. 12x. So here x squared plus x and minus 2, yeah? So here we can, actually here we need to write it at two factors. So here x squared plus x minus 2. So how to find the factors? Actually here we can see here this constant, okay? This constant at the x squared here is 1. So 1 we can write it 1 times 1 here. 1 equal to 1 times 1. And the constant here is minus 2. Yes? In minus 2 we can write it to minus 2 times 1 or 2 times minus 1. Okay? So here we can see here is 1. So here if we write here is minus 2, 1. So here is 2 times minus 2 plus 1 is minus 1. So minus 1, but here is 1. So here actually this cannot. Okay? Now we use the second. Here is 1. And here is 2 times minus 1. 2 times minus 1. So here is 1 times 2. 1 times 2 plus 1 times minus 1. So 2 plus minus 1. So here is 1. So here is 1 and this constant, they are the same. So this work, okay? This work. So here means here the first factor here is 1x plus 2. The second factor is 1x minus 1. So 1x minus 1. So 1x actually is x. So here we can rewrite it in this form, okay? So here equal to what? 12x x minus 1 or x minus 1 x plus 2, yeah? So here we can write it in this form, okay? In this form. So in this form, now we can see it's positive or negative. So here we can see first we let it equal to 0. First we let it equal to 0. We can find x equal to 0. X. So here, okay, here I think that we should here first we let g prime equal to 0. We can find x equal to 0, x equal to 0, or x equal to 1, or equals to 1, or x equal to -2. Yeah. So here we have 3 points. So here we plot the x coordinate. So here is -2, and here is 0, here is 1. So here now this 3 points. So we have 4 parts. We have four intervals. Okay. The first interval is -infinity to -2. The second interval is -2 to 0. The third interval is 0 to 1. The fourth interval is 1 to infinity. So here we listed the table. The first is intervals. So the second is f prime. The third is convolution. So here the first interval is -infinity to -2. So when x, now we can see when x less than -2, this here is positive or negative. Here is negative, yeah? X is negative. X -2 is negative or positive. When x less than -2. Here? Negative, yeah? Here is also negative. So when x less than -2, x plus 2 is negative or positive? Negative, yeah? So here is negative number times a negative number times a negative number, so it's negative or positive? Negative. So here is negative, yeah? Negative. So here means f prime. Oh, no, I'm sorry. Here is g prime, okay? G prime. So g prime less than 0. Less than 0, so here is decreasing, yeah? Decreasing. So this is the first interval. The second interval here is -2 to 0. -2 to 0. So here, when x greater than -2 but less than 0, so here this part is negative or positive? Negative, yeah? Here is positive or negative? X. When x is in this interval, so x -1 is positive or negative? Also negative, yeah? Also negative. And when x in this interval, x plus 2, negative or positive? Positive, yeah? So you can see -2. So you can take, for example, you can take a number -1. -1 plus 2 is great, is 1. Positive, yeah? So here is positive, okay? A negative number times a negative number times a positive number. So it's positive, yeah? So here is g prime is greater than 0. Greater than 0, so here is increasing. So here is increasing. So the third interval is 0 to 1. Okay, 0 to 1. So 0 to 1 here is positive. Here? Positive? 0 to 1. In this interval, x -1. Negative, yeah? Negative. And 0 to 1 here? Positive. So positive times negative times positive. So here is negative, yeah. So G prime less than 0, so here is decreasing. And the last interval 1 to plus infinity. 1 to plus infinity, of course, here is positive, here positive, yeah, positive, here positive times positive, so of course it is positive. So G prime greater than 0, so here is increasing. So if now, so of course, now so we have this information. Okay, if we have this information, so we can plot the graph of this function. A sketch, okay, or a sketch. So here we can see here is decreasing. So here means decreasing, and minus 2 to 0 is increasing, and 0 to 1 is decreasing, yeah, and here 1 to plus infinity decreasing. So it's actually like this, a sketch, okay. Just a sketch. Like this. So I think that it's easy. Okay, it's easy. So now do access. Now, for example, for here is 3x cubed minus 12x and plus 7. Okay, for this function. Find the interval is increasing and decreasing. Okay, now do it. I hope that every you should list a table, okay? A table like this.
Just only on fx?
Yes. Fx equal to 3x squared minus 12x plus 7. So here for this function, you find the intervals on which is increasing and on which is decreasing. So it's easy, okay? equal to 0, so we can find x equal to what? No, f prime equal to 0, so x equal to what? 2. Yeah? So 2. You plot 2. We have a positive. So the minus infinity to plus infinity, we have two parts. Minus infinity to plus infinity. Yeah. Six actually it doesn't matter, okay? So here is here. So increasing here, increasing here. So you just need to see f prime equal to 0. So you can see that 2. The point on the x coordinate 2. So we have interval minus infinity to 2 plus I will last, okay?
The same that I'm trying to get is that x prime So we can say x is greater than 1 because 2 minus 2 is greater than 0. That's what we say. If x prime is supposed to be 1, x is supposed to be 3. So 3 minus 2 must satisfy that thing. That's what I think. The papa is not saying that the papa is different. No, it's
Just have to choose number
let's say x prime is equal to 0. Then what is x must satisfy the answer as x minus 2 is equal to 0. So meaning of x will be 2. Hence, in the line, knowing that e equals 0, so minus infinity to that minus infinity to let's say what is the
at this place at this time from last week. Okay. So here. Now let's see this question. Okay. So I think the first is find the derivative. Find the derivative. So f prime equal to what? Equal to 6x minus 12 plus 0. So here the 6x minus 12. So we can write it 6 times x minus 2. Yeah. So the first step you should to let it to 0. Let f prime equal to 0. Let f prime equal to 0. You can see x equal to what? X equal to 2. Yeah. X equal to 2. So you plot the point on the x coordinate. Okay. On the x coordinate. So here is 2. So this point. So okay, this point we decompose the x coordinate to 2 parts. The first part is on the left of 2. The second part is on the right of 2. So the first part actually is the interval. So the interval is what? Is minus infinity to 2. This is the first interval, okay? And the second interval is 2 to plus infinity. So here f prime. So here this part we can see f prime actually is less than 0. Yeah. So the conclusion actually here is decreasing. And here f prime actually in this part is greater than 0. Yeah. Greater than 0. So here is increasing. And now I found some students have confusing at how to find the intervals. Okay. How to find the intervals. For example, we have a function. The derivative of a function equal to x minus 1 times x plus 2 or x minus 3. So here, actually, okay, for example, we have a function. The derivative of the function equal to this. So how to find the intervals? The first step is you let it equal to 0. Okay, you let the f prime equal to 0, and then you find here x equal to what? X equal to 1 or 3. Yes? 1 or 3. So you plot these 2 points on the x coordinate. Okay? So you plot the here is 1, here is 3. Yeah? So you can see these 2 points. These 2 points, okay, decompose the x coordinate to 3 parts. 3 parts. The first part is on the left of 1. The second part is on the left of 1. So here is minus infinity to 1. This is the first interval. The second part is this part. This part is on the right of 1 and on the left of 3. So here is 1, 2, 3. This is the second interval. Okay. The third is on the right of 3. So the third interval is 3 to plus infinity. So here this is the interval. Okay. So this is the method to find the interval. Okay, find the intervals. So here this is this part. Now. So we come to the second part of the concavity, okay? The concavity. The concavity, okay? So the concavity, so now first, the increasing or decreasing is enough to describe a function. For example, okay, if I give you, I tell you that it's increasing or decreasing, this information, okay, actually is not enough to describe a function. For example, we can see here, like this function, okay, here is increasing, yeah, here is also increasing, yeah, also increasing. But for these two, okay, they are not the same, okay, they are not the same. We can see here for the first here, we can see the tangent line, okay, for any point, the tangent line is less above the graph. For here, for this graph, okay, the tangent line, okay, the tangent line of the point is less above the graph. But for here, you can see the tangent line actually is less below the graph. Less below the graph. So here means actually they are the same. They are all increasing. They are all increasing, but they are not the same. Okay, they are not the same. So here we need to give another definition to describe the functions. Okay, so here for this we need the concavity. Okay, the concavity. So here now let's see a graph like this here. For this function, y equal to x squared, for this function, we can plot the graph. We can plot the graph. We can plot the graph. So here, this is the graph y equal to x squared. So we can see for this graph, okay, for this graph, you can see the tangent line. The tangent line actually is on the left. You can see here, the tangent line actually on this point is less below the graph, and on this point here is also less below the graph, and here on this point we can see the tangent line is also less below the tangent, the graph. So here means for this graph, okay, we have a factor. The factor is the attached line. The attached line lies below the graph. That's below the graph. This is the first factor, okay? Actually, we have another factor, okay? We have another factor. The another factor is, you can see here at this point. At this point, for example, this point is -1. This point is -1. This point is 0. And this point is 1. For example, we can see at this point, the slope is what? This tangent line, the slope is what? The slope actually you should to find the derivative fx equal to x squared. So f prime equal to 2x, yeah, 2x. So here we can see f prime equal to x equal to -1. Here equal to -2, yeah. And f prime 0 equal to what? 0. And f prime 1 equal to what? Equal to 2, yeah? So here we can see, here the left is negative, here is 0, here is positive. So we can see the f prime actually is increasing. -2, 0, 2. So actually the f prime is increasing. This is the second factor, okay? The second factor here is the f prime here is increasing. This is the second factor, okay? So for a function, okay, for a graph, we have this factor or have this factor. We call it at what? We call it at concave up. Concave up. So here, if a function have this factor, okay, have this factor or this factor, we call it concave up. Concave up. So here now we can see the another function for y equal to -x squared for this function, okay. For this function, we can plot the graph. Here is x, here is y, here is the origin. So here, the graph actually like this. So it's easy, okay? It's easy. So you can see, for example, for this -1, the hatched line actually is like this. And at the 0, the hatched line is a plane. And at the point 1, the hatched line actually is like this. So here we can see the hatched line actually is less up, yeah, less up the graph. So the first factor is the hatched line. The hatched line less up. Oh no, I'm sorry. That's above, okay? That's above the graph. That's above the graph. So this is the first factor. The second factor here for this function, okay? This function we let it gx. So we can see g prime equal to what? G prime equal to -2x. -2x. So here we can see g prime at -1 equal to what? Equal to 2, yeah? And g prime 0 equal to what? 0. And g prime 1 equal to what? -2, yeah? So here we see 2, 0, -2, so it's decreasing. G prime is decreasing, okay? G prime is decreasing. So here means what? G prime is decreasing. So here, if a function have this factor or have this factor, we call it the function is concave down. Okay, concave down. concave down. So here, this is concave up. This is concave down. Concave up actually is F prime is increasing. F prime is increasing means what? So we just say increasing means the derivative of this function is positive, yeah? It's positive. So the derivative of prime, F prime is positive. So actually here, this function is increasing. This function is increasing means the derivative of this function is positive. So the derivative of this function is what? F prime derivative. So it's F prime prime, yeah? So F prime, the second derivative. The second derivative is greater than zero, concave up. So here it's the same. G prime is decreasing means the derivative of this function is less than zero. So the derivative of this function is what? Is G prime prime, yeah? G prime prime. So here is G prime prime x is less than zero. If the second derivative less than zero, concave up, concave down. So here we have. So here we can see the definition. The definition, okay. So now let's see page 213. 213. Oh no, 212. Sorry, 212. 212. We can see the definition 5.1.5.1.3. Okay, 5.1.3. The definition, if f is definable, if f is definable on an open interval, this open interval we use I, okay, I to denote. Then f is set. Then f is said to be concave up. Then f is said to be concave up on I if f prime is increasing. If f prime is increasing on I, okay. And f is said to be concave down on I if f prime is decreasing. So this is the definition, okay? This is the definition. The definition we use the second factor, okay? The second factor. So here means f is definable on an open interval I. Then f is said to be concave up. Concave up means f prime is increasing, okay? F prime is increasing, concave up. F prime is decreasing, concave down. So just remember this, okay? F prime is increasing, concave up. F prime is decreasing, concave down. Okay, concave down. So I think that you just remember this, okay? Just remember this. F prime increasing, concave up. F prime decreasing, concave down. So just remember this, okay? Yes. I think it's easy, okay? You just remember here, okay? This point, this is the key point, okay? Yes. So here means actually, so we can see f prime is increasing on I f prime is increasing. A function is increasing. How to determine a function is increasing? We just need to see f prime, the derivative of f prime. Yeah. So here we have f prime is increasing on I, means f prime is greater than 0. F prime is greater than 0, so f is concave up. So here f prime is decreasing on I, means the derivative of f prime is less than 0. So f prime less than 0, concave down. So we have this result, okay? So we have a result. So here now, let's see, we have this result. Let f be twice definable on an open interval I and open interval I if f prime greater than 0 for every value of x in I. Note that every value, okay? Every value in I, okay? So then f is concave up on I. And if f prime less than 0 for every value of x in I, then f is concave down. So how to determine concave up, concave down? Just need to see f prime. F prime positive, concave up. F prime negative, so concave down. Yeah. So I think it's easy. Yeah. So it's so easy. So actually, the content of this class, actually, we just need to see one sentence, okay? One sentence. The sentence is what? Is if f prime greater than 0, increasing. Yeah? And f prime less than 0, decreasing. Yeah? And f prime greater than 0, concave up. And f prime less than 0, concave down. So here just this sentence, okay? So it's so easy, yeah? Yes. So remember it, okay? Remember it. The information of the first derivative to see the increasing or decreasing. The information of the second derivative to see the concave up or concave down. So now, okay, I give you an example. So for the function fx equal to x cubed minus 3x squared plus 1. For this function, to determine the intervals on which f is increasing, decreasing, concave up, concave down. Okay, concave up, concave down. So here now let's see. We can see increasing, decreasing. See the first derivative, the first order derivative. So we can see f prime fx equal to x cubed minus 3x squared plus 1. For this function, the first derivative f prime equal to what? 3x squared minus 6x plus 0. Yeah. So we can take out 3x. 3x times x minus 2. Yeah. So here we can see we let it equal to 0. We let it equal to 0. So we can see x equal to 0 or 2. Yeah? So x equal to 0 or 2. So 0 or 2 we plot it. Here is 0, here is 2. Yeah? So the point 0, 2, we decompose the x coordinate into 3 parts. The first part is minus infinity to 0. The second part is 0 to 2. The third part is 2 to infinity. So here we list a table. So intervals, and here is f prime. Here is the convolution. So here intervals. Here is minus infinity to 0. So minus infinity to 0, the f prime is. So if you cannot to determine is positive or negative, I think that we have a easy method. Okay, you just choose a number in this interval. For example, you choose minus 2 in this interval. Yeah. Minus 2. So minus 2, you can see x equal to minus 2. So x is negative. Yeah. Negative. Minus 2, negative. Negative times negative. So positive. So here means f prime positive. Positive. So here is increasing. Yeah. And the second here is 0 to 2. Yeah. 0 to 2. So you choose a number in this interval. 0 to 2. We choose 1. Okay. Yes. We choose 1. So here is 1 positive. Negative. Positive times negative. Negative. Yeah. So here is f prime less than 0. So here is decreasing. And the third part is 2 to plus infinity. 2 to plus infinity here is also you choose a number, for example 3. So here 3 positive. 3 minus 2 1 positive. So positive times positive. Yeah. So it's positive. Yeah. So f prime greater than 0. Yeah. So it's what?
It's easy to see.
So here is increasing. Yeah. So it's increasing. So here we find the intervals on which it's increasing and decreasing. So the second is which we need to find the intervals concave up, concave down. So concave up, concave down, we need to see the second derivative. So the second derivative, f prime, okay, f prime equal to what? Equal to f prime, yeah? So f prime is, so we need to find the derivative of this function. 3x squared minus 6x. So the derivative of this function is what? 6x. 6x minus 6. Yeah? Minus 6. So it's equal to 6 times x minus 1. Yeah? So the same. Okay, we let it equal to 0. We let it equal to 0, so we can see x equal to 1. X equal to 1. So here 1 decompose the x coordinate to 2 parts. The first part is minus infinity to 1. And the second part is 1 to plus infinity. So here we can see the intervals, and here is f prime prime. Here is the conclusion. So the intervals here is minus infinity to 1. So minus infinity to 1 here is f prime prime. When x less than 1, here is positive or negative? Negative, yeah. So here f prime prime less than 0, So here is concave down, yeah. Concave down. And here is 1 to plus infinity. 1 to plus infinity here, where x belongs to this interval. Of course, here is positive. So f prime prime here is greater than 0. So here is concave up. So this is the answer. Okay, this is the answer. So here we, according to this result, we can plot the graph of this function. So here now we can see
This place.
we have the point. We can see 0, 0, 2. Okay, 0, 0, and 2. And the point 1, okay, the point 1. These 3 points, okay. So first we can see minus infinity to 0, the function is increasing, and in this interval is concave up or concave down. So we can see concave down, yeah. So increasing. So here increasing and concave down, okay. So increasing and concave down. So it's like increasing here like this. Yeah. Here is concave up, concave down.
No.
Here is concave up.
Yeah.
So here concave down means yes.
I think
It's from 0 to 1.
we first make increasing, decreasing, then to give us concave down or concave up. Because we say if the fraction is increasing, means it's concave up.
No. Here means f derivative increasing, concave up. Yeah. So increasing means this function, okay? So I just see increasing. For example, for this is increasing. Here is also increasing, but here is concave up. Here is concave down. Yeah. So here actually. Oh, I'm sorry. Here is concave up. So I think concave up or concave down. You just use the the second derivative. Yeah. So I think here, if the how to remember it? Okay, how to remember it? The first is the second derivative greater than 0, concave up. Yeah. The second derivative less than 0 concave down. Yeah. But how to pronounce concave up, concave down? Up means the graph is up. Up the titled line. So you can see here the for this graph, the graph is less down the titled line. Yeah. So here this is concave down, and here we can see the graph is less above the titled line. Yeah. So the graph. So here this is concave up. Okay. Here is concave up. Concave up means the graph less above. Less above. And the concave down means the graph less down, okay? Less below. So here we can see in minus infinity to 0, is increasing and concave down. So here actually is like this. Like this. And to 0 to 1, we can see 0 to 1 is here, is decreasing, and 0 to 1 is concave down. Yeah, concave down. So here is like this. And 1 to 2, okay, in this interval, first is decreasing, and 1 to 2 is concave up. Concave up means at this point, the left is concave down, the right is concave up. So like this. Okay. So here, on this part, on the point 1, on the left is concave down, on the right is concave up. So here the graph actually like this. Like this, okay? So like this. And from 2 to infinity is increasing and concave up. So here like this. So we can see it's not one step, but we can see the page 213. We can see the figure 5.1.9. Okay, 5.1.9. 5.1.9. We can see the graph like this. Okay, like this. 5.1.9. The finger 5.1.9. Okay. So here. Now, okay, let's see this point. This point, okay. This point. Okay, listen to me, okay. Only 5 minutes. Only 5 minutes left, okay. So on this point, the left is concave down, the right is concave up. The left is concave down, the right is concave up. So for this point, we have a name, okay? We have a name in mathematics. This name is inflection points. Inflection points means what? On this point, the left is concave up, right is concave down. Or the left is concave down, right is concave up. Means the concavity left and right, this point, they are different. Okay, they are different. So we have a definition of the inflection point. Okay, inflection point. So we can see. So okay, here we have the definition. If f is continuous on an open interval containing a value of x0, if f changes the direction of its concavity at the point x0, ff0, then we say f have an inflection point at x0. So this is the definition, means what? At this point, changes the direction of its concavity. Okay. So here means, for example, this is x0. If the left is concave up, the right is concave down. Concave down. This is the first case. Okay. The first case. If on the left of the point x0 is concave up, and on the right of the point is concave down, then we see x0 is the inflection point. Yeah? And the second case is on the left is concave down, and on the right is concave up. Then we also say x0 is inflection point. Okay. So here means at this point changes the direction of its concavity. Okay, concavity. So here this is the definition. Okay.
Yes, sir.
Yeah.
No, I'm agreeing. Yes, sir.
So here now, I have an example. So I'm sorry, I just need 5 minutes. Okay. Now, okay, we see this example. For function fx equal to x plus 2 sin x in this interval, okay, 0 to 2 pi. Now, in this interval, we find the intervals on which is increasing, decreasing, concave up, concave down, and find all inflection points, okay, inflection points. So just do this thing, okay. Do this thing. So here, actually they are the same, okay. So f prime equal to what? F prime equal to 1 plus 2 cosine x. Yeah, 2 cosine x. So first we let it equal to 0. We let it equal to 0. We let it equal to 0. So cosine x equal to what? Cosine x equal to minus 1/2. Yeah. So x equal to what? Now we first, I think that we need to record the graph of cosine x in this interval. In this interval, the graph of cosine actually is like this. Here is x, here is y. So here is 2 pi, here is 2 pi. Here is fx, or here is y equal to cosine x. Here is 1, here is pi. So now, so in this interval you find cosine x equal to 1/2, x equal to what? 1/2 actually here is -1. So 1/2 actually is here. So actually we have 2 points. The first point here, the second point here. So this whole point is what? Cosine what? Equal to -1/2 here. What? This point. This point and this point. We have 2 points. The first point here, cosine this point equal to 1/2. This point also 1/2. So I think that you should remember the sine cosine of some usual angles. Okay, some usual angles. So cosine what equal to 1/2? Actually, we know cosine 2 pi by 3. Okay, 2 pi by 3 equal to 1/2, and cosine 4 pi by 4 or 4 pi by 3 also 1/2. Okay, 1/2. So here we have 2 points. For the first is 2 pi by 3. The second is 4 pi by 3. Okay, 4 pi by 3. So from here we have. Here is 0 to 2 pi. Here is 2 pi by 3. Here is 4 pi by 3. So we have one interval, second interval, the third interval. So we have 3 paths. Okay, the 3 paths. So we have 3 paths. Here the interval and the f prime and the conclusion. So interval here is 0 to 2 pi by 3. 2 pi by 3. So here we can see 2 pi by 3 here. F prime is greater than 0 or less than 0. So here actually you just need to choose a value in this interval. We can see actually here this is greater than 0. Yeah, greater than 0. We can see you can choose this point. Okay, this point we can see cosine equal to 0. Cosine equal to 0. So here is 1. Yeah, so it's greater than 0. So here is increasing. And now we can see 2 pi by 3 and 4 pi by 3 in this interval. Okay, in this interval actually in this interval. Okay, in this path we can see cosine is less than -1/2. Less than -1/2. For example, -1. So cosine equal to -1. 1 plus 2 times -1. Of course, is less than 0. It's less than 0. So here is f prime less than 0. So here is decreasing. Yeah. And 4 pi by 3 to 2 pi. In this interval, actually, is in this part. In this part. Of course, in this part, we can see the cosine is greater than -1/2. Cosine greater than -1/2, so 1 by 2 cosine is greater than 0. Greater than 0, so here is f prime greater than 0. So it's increasing. So this is the increasing, decreasing, okay? So concave up, concave down. So we need to find the second derivative, okay? The second derivative, so f prime prime x equal to what? Here we find the derivative of this function minus 2 sin x, yeah? Minus 2 sin x for this function, okay? For this function, the same, okay? That is equal to 0. That is equal to 0. Find x equal to what? So here, from here, we can see sin x equal to 0, yeah? Sin x equal to 0. Now we first remember here the graph of sin. Actually like this, yeah? Here is x, here is y, here is 0, here is pi, here is 2 pi, here is 1, here is minus 1, yeah? So we can see the point is pi, yeah? The point is pi. So here, actually we just see the open interval, okay? So open interval 0 to 2 pi, okay? So here means x equal to pi. X equal to pi. So here we can see here is 0, here is 2 pi. So here is pi. So we have 2 parts. The first part is 0 to pi, the second part is pi to 2 pi. So here we have the interval and the f prime prime and the conclusion. So the interval we have 0 to pi. The second interval is pi to 2 pi, okay? So on the first interval, 0 to pi, we can see from 0 to pi, sin is positive. Sin is positive, so a positive times minus 2. So it's negative, yeah? Because here minus 2 is negative. Sin x in this interval is positive. So it's negative, yeah? So here is negative. So here negative means what? It's concave down, yeah? And in this pi to 2 pi, in this interval, pi to 2 pi, we can see the function actually, the sin x is negative. Negative times minus 2. So minus 2 times a negative, so it's positive, yeah? Greater than 0. So greater than 0, so of course it's concave up, yeah? So from here we can see on the left of pi is concave down, on the right of pi is concave up. So pi is what? Is the inflection point, yeah? So pi is the inflection. So pi is the inflection point of the function. Okay? So this is the answer. So actually, I think that the one sentence of this class is f prime greater than 0, increasing. F prime less than 0, decreasing. F prime greater than 0, concave up. F prime less than 0, concave down. Okay? So the class is over. Thank you.
Thank you.